Okay, today I shall be discussing the topic of the Turing machine, the most powerful of the mathematical models of the machines that we have studied so far. So this is the most powerful machine that we can have. We studied that DFAs can compute for the regular languages, but then they have the limitations. And then we saw that, okay, some of those limitations could be removed with the help of the PDAs. And then later on, when we were discussing the pumping lemma for the context-free languages, we had seen that PDAs also have their limitations because there are languages which were outside the scope of the computation of the PDA. So we get to the domain of the Turing machines, and there is no machine that is powerful than Turing machine. If some problem is not computable by Turing machine, then that problem is intrinsically not computable. For the time being, what we have that DFAs have of their limitations, they can go for the languages which are the regular languages. Then if a language is not a regular language and it is a context-free language, then it comes in the domain or in the power of the computation of a PDA. A and B and was one language. This can also be considered as the delimiter matching language. I would want to see, okay, if there are n left open parentheses, then I have got right open, then yeah, right closed parentheses as well. So left parentheses are matched by the right parentheses and they are linearly intervened with one another. And another example was WWR length, even length palindromes. That is also under the domain or under the power of the computation of a PDA. Then we have this language with us, A and B and C N. What happens if we have got three characters in their respective trains and we would like to know if the quantity of each character is the same in all of the trains. It cannot be done with the help of the PDA, but it can be done with the help of a Turing machine. We will construct a machine for this language as well. And then this the copy language. So it means that is there some way in which you can find out that given string is a copy of two equal substrings. So it is not computable by the DFA, by the PDA as well. It is only computable by the Turing machine, and we are also going to create a machine for Turing machine for this language as well. So let's get started with the Turing machine concept. And this is the schematic representation of Turing machine. Now the just like every machine that we have studied so far, whether it was a DFA or it was a PDA, there is an input tape. But this time, this input tape is infinite on the left as well. For the PDA as well as the DFA, the input tape was only infinite towards the right. But this time, this input tape is infinite towards the left as well. Okay. So, and another thing or another difference between the Turing machine and the other machines so far is that the reading head of the control unit is also the writing head. What does that mean? That means, okay, Osama has asked me a question. Let me answer to your question. G. Osama Afzal.
Sir, I wanted to ask, you said it is unlimited from both sides. Does that mean you can input the symbol from both right and left?
Okay, when I say that it is infinite on the left as well as on the right, now that means, first of all, whenever we start a computation, there would be some string on the tape. And at the beginning, when the machine has to start its computation, there is not going to be any blank cell in between the characters of the input string. The characters of the input string are going to be placed, would be concatenated next to each other. There is not going to be no blanks allowed. Okay. And then when I say that, okay, this tape is infinite, first of all, it will locate, okay, the cell from where the string starts. And then it has the opportunity of moving towards the left hand side and writing something on it if required. And when I say that it is infinite on the right hand side, it would mean that the read write head of the Turing machine can hover over the tape and reach to the end of the string and if there is something to be written at the end of the string, it has the possibility of writing some symbol onto that particular cell as well. So at the beginning, the input to the Turing machine is on the input tape, and that string has no blacks in between. It is just one consolidated string. So I hope that answers to your question, Osama. Is that clear? Okay. Please do not write your attendance right now. By the way, Khaja Abdul Ahad and Said Mozam Ali, both of you have not written the attendance in the format I had asked you guys. Please don't do that. Just see the pattern and then put in your attendance. Not now when I will signal it. Don't do that, please. Khaja Abdul Ahad as well as Sayyid Muhammad Kazmi. Please don't do that. Okay. So I hope that I have answered your question, Osama. Yeah, so you are okay, fine. So that was the left hand infinity and the right hand infinity. By the way, I'm also going to discuss further variants of the Turing machine, and we shall see that it does not matter if we have an infinite tape or if we have a semi-infinite tape. So the terminology semi-infinite tape means that the tapes that we have been dealing with so far, which means the input tape for the DFA was semi-infinite because there was a left end to it, but there was no right end to the tape. And similarly, the PDA had the semi-infinite tape, it had a left end, but it did not have the right end. And we do not have any stack for the Turing machine, because if at all it has to use something, if at all it has to write something, it has this entire tape available with it. So if at all it wants to keep record of something, or or keep the history, so it can always use the blank cells of the tape. Okay, but most of the time we shall be seeing that whether machine is writing onto the tape or it is reading from the tape, this reading and writing, the characters of the I should say that the characters of the string are always they do not have any blacks in between. Okay, there can be blacks, but we prefer that there are no blacks in between the characters of the on the input tape. Now, when we talk about this no bound, the infinite tape, it means it has no boundaries. The head can move towards the left indefinitely, and it can move towards the right indefinitely. So theoretically, that is what we shall be dealing with. So uh, the responsibility of not the responsibility, the function of the read write head for the Turing machine is this one. It can read a symbol from a cell, it can write a symbol onto the cell, then it can either move to left or to the right. By the way, once again, we have another difference between the Turing machine and the reading heads of the DFAs and the PDAs. In case of the DFAs and PDAs, the reading head is always moving from left to right, reading the string as we would read in a humanly way. But the read write head of the Turing machine can also move towards the left as well, or it can zigzag in between these strings, so it can move left or right or left or right. So that is the flexibility available with the read write head of the Turing machine. So here is one example. Suppose the contents of the input tape are A, B, A, C, and read write head is at the symbol A, which happens to be the third cell of the input string. And if the movement is this one, that the read write cell reads an A, it replaces it with the symbol K and moves one cell to the left. So there would be an instruction in the Turing machine, or there would be an instant of the transition function for the Turing machine, that if there is some active state and the input tape and there is the new symbol to be read is the symbol A, replace it with K and move one step left. So that is just one example of what is going to happen if we have such a configuration in a Turing machine. Osama Afzal has another question. Okay, G Osama.
Sir, what is the difference between a transition and a time step?
Okay, transition and a type step. Okay, when I talk about the transition, it means that there would be some state, say for example qi, and the transition function says that if the active state is qi and the symbol to be read is a from the input tape, then transit to state qj, write k instead of a, and move one step left as yeah, and the head is to move one step left. So that happens to be the transition. When I talk about the time zero and time one, the time step that you have referred to, time zero mean, okay, this is the instantaneous configuration of my Turing machine when it had to read a, and after it has read the a, that is the next step configuration of the Turing machine. So time zero means before the transition taking place, time one means after the transition has taken place. Moreover, notice that maybe the machine has not come to a halt, which would mean that okay, it has to do a bit more of its functions. Then time one would mean that okay, that there is another transition possible, and then there would be time two as well. Maybe there is a time two. Let me check. Yeah, there is a time two as well. So in at time one we have got a b k c. The read write head of the machine is on the second cell of the string, and the character to be read is b. Now suppose that there is a uh, there is a there is transition available, or there is a transition programmed in the Turing machine. So that would be that replace b with f and move one step right. So at time two, this is going to be the configuration of my Turing machine. I hope that answers to your question. Okay. Now the input string. Yeah, as I've said earlier, we shall always see that the input string is written on the input tape without any blanks in between. So A, B, A, C. It shouldn't be the case that your input string is divided into two substrings. Say for example A, B, and then there is a blank in between, and then the next is AC. No. As far as the input string is concerned, you always have to place it in the consolidated form. So machine would start, if at all machine hovers over it, it will hover over for four cells, and then it would know, okay, this is the scope of the input string. Moreover, for the time being, we do not know how does machine knows the okay, machine know the length of the string, but it knows the scope in the sense that when it starts moving towards the left hand side and it encounters a blank cell, it would know that okay, this is the left end of my string. And when it hovers over the string and moves towards the right hand side, and it encounters the empty cell, it would know that it has reached the right end of the string. So the entire string is delimited by the empty cells on the left as well as empty cells on the right as well. So that is how machine would know the scope of the input string. Now, oh, what is happening, during the states transitions of the Turing machine? Uh, it has to read, it has to know what is the active state, and it has to know what is the new symbol to be read. These are the two input arguments for the transition function of the Turing machine. And in the return, machine has to know what is going to be the next active state, the first thing. Second thing, it has to know, okay, if at all okay, what is the symbol to be read. And the third thing is that what is the symbol to be written. And then the fourth thing is, okay, whether the head has to move towards the left hand side or towards the right hand side. Okay, this reading and knowing the previous active state, this happens as an input. So as an input, the transition function requires two things: the active state, the present active state, the current active state, and the symbol to be read. And as an output, it is going to tell you what is the symbol to be written instead of the symbol read, what is going to be the next active state, and what is going to be the next position of the head, whether it has to move left or towards the right hand side. Now, the domain of the Turing machine is Q cross sigma, and the codomain for the transition function of the Turing machine would be Q cross gamma cross LR. Okay. So, well, it will be clear next as well, but I wanted to know if you can guess it for yourself. Now I have got two instances of the transition function over here. Now I have got two instances of this some generic Turing machine. Now this instance says if Q1 is the active state and A is the symbol to be read from the input tape, go to the state Q2, replace A with B and move the head one step left. And this instance says that if the active state of the machine is Q1 and the symbol to be read from the input tape is A, go to the state Q2, replace the symbol A with the symbol B and move the head one step left. By the way, in each step of the transition or in each step of the computation, the Turing machine can always move one step left or one step right. It cannot jump 2 steps or 3 steps or 4 steps. No, that is not going to happen. For the standard Turing machine, there's no jumping allowed. The head will always move either one step left or one step right from its previous. So let's see. Uh, we have one instant of some Turing machine. It says that if Q1 is the active state, A is the symbol to be read, then go to state Q2 and replace that A with a B and move one step right. So let's see what happens in this case. We have A, B, A, C as the contents of the input tape. The active state of the machine is Q1 and A is the symbol to be read from the input tape. This arrow signifies the present location of the read write head. Now my transition function says that replace this A with the B, go to state Q2 and move the head to the right. So in time 2, I should have A, B, B, C, and the arrow should be beneath the letter C because the read write head has to move one step to the right hand side, and the active state of the machine is going to be Q2. This must happen, and voila, that is there. I have got the contents of the tape are changed from ABAC to AB square C. The read write head is on the fourth cell of the string and the active state of the machine is Q2. It is on the fourth cell because the head has moved one step towards the right hand side as was prescribed by the transition function. Here is another instant. Let me see. Yeah, here's another instant. Now this instant says that if the symbol to be read from the input tape is A and Q1 happens to be the active state of the machine, replace that A with the letter B and move one step left. So when I look onto my input tape, I have got A, B, A, C. Next symbol to be read is A, active state of the machine is Q1. Therefore, this A is to be replaced by B and the head is going to move one step towards the left hand side. So I must have A, B, B, C and head must be there on under the B, and then the transition function also says that Q2 is going to be the next active state, and that is also happening over here. So that was the demonstration of how the transition functions behave. Now what does that say? Now this transition function says that if during the state of if during the chain of computation uh, the read write head appears or happens to read an empty cell, the transition function says that, okay, write G onto that empty cell and move one step right. So machine is writing G over here and move one step right. Okay, the active state, the next active state is going to be Q2, and there I have Q2 with me, the next active state. So I told you guys that, okay, machine has infinite tape. It has the possibility of writing or availing those cells. So in this case, we can see at the beginning that the length of the contents of the tape was 4, but now the length of the content of the tape is 5. Okay, I have discussed this thing. Now, as was discussed already, the Turing UMAD, as it was discussed already, Turing machines are always deterministic. They are not non-deterministic. So it would mean the subsequent transitions of this type are not allowed, where you are allowing the possibility that if Q1 is the active state and A is the symbol to be read, on one branch of the computation, machine is going to go to state Q2 and write a B and move one step right. and on the other branch of the computation, machine is going to go to state Q3, write a D and move one step left. No, this is not allowed. However, if you are looking at this side, this is totally deterministic stuff. For one input, it has a unique output. Now, for one input, it has multiple outputs in the non-deterministic version. But for the deterministic version, for one input, it has a unique output. QA means go to Q2, write a B, move one step right. Q1B means go to Q3, write a D, and move one step left. And up, and no epsilon transitions allowed in the deterministic machine. Uh, Partial transition function. Okay, there is a concept in mathematics, and that concept is known as a total function and a partial function. Okay, now when I talk about the total function, now total function would mean that the function is defined for every element of the input, and partial function would mean that the function is defined for not every member of the transition function of the Turing machine being a partial transition. By being a partial function, it would mean that it is the same. If you guys remember, I discussed one concept, and that was the incomplete DFA. That Q1A, there is an output for Q1A, there is an output for Q1B, but there is no output for Q1C. Now, in terms of the functions, I would say that this is a partial function. But in terms of the computations, I would say, well, if the active state of the machine is Q1 and next symbol to be read is C, then there is no possible computation for it. Maybe it might go to the accepting state, it might go to the rejecting state. It will depend upon the fact that what is Q1. Is Q1 an accepting state or a non-accepting state? So what I'm saying is that suppose if Q1 was an accepting state and there is a C coming in, now the computation would end and Q1 would remain the Q1 would remain the active state. If since it is an accepting state, therefore the string would be accepted. Otherwise, we might have the case that okay, if there is a C and this is not an accepting state, we would say that the input string is rejected. Okay, now let's move one step forward. When we talk about the halting, when do we say that the machine halts? We would say that machine would halt when there is no transition possible. As in this case, the active state of the machine is Q1 and no transition is defined for any input symbol. So that is there. It is machine would halt. As I said, the computation ends. So this is one possibility when we would have a halting. Another possibility of halting is the same story, that the active state of the machine is Q1, although there are transitions defined at Q1, but those are for the symbols A and the symbol B. For symbol C, no transition is defined. Therefore, it is a halting configuration. And what else? Yeah, we have this thing with us as far as Turing machines are concerned. We will not allow outgoing arrows from the accepting states. So if machine lands onto the accepting state during the computation, it will just remain there. It will not perform further computations. And it would mean that Turing machine is the kind of machine which can accept a string without emptying the input tape. As far as the DFA and the PDA were concerned, we said that their computations would end when the input is empty. But this is not necessary for the Turing machine. If during the computation, machine transits to one of the accepting states, then that's it. That string gets accepted because I do not have any outgoing transitions defined for the Turing machine. Okay. Yeah. So accepting an input would mean that okay, the machine halts in an accept state, and reject an input, it would mean either the machine halts in a non-accept state or the machine enters in an infinite loop.